Okay, so what if I told you there was a cheat code for science? A way to run experiments that are just too expensive, too slow, or, well, physically impossible. It sounds like science fiction, right? But a really powerful AI technique is doing just that. It's letting researchers simulate the impossible, and it's supercharging the pace of innovation. So let's dive right in and see how it works. All right, here's our game plan. We're going to start with a huge, almost impossible problem in the world of microchips. Then we'll get into the amazing AI solution. It's kind of like teaching a computer how to dream. After that, we'll see if this dream actually holds up in the real world. Then we'll zoom out a bit and see how this idea is changing everything from particle physics all the way to medicine and what it means for the future. So, first up, the nanoscale gamble. You see, to really get why this AI solution is such a big deal, you first have to understand just how incredibly, mind-bogglingly difficult it is to build modern electronics. I mean, just look at this number. A modern computer chip is an absolute marvel. We're talking more than 25 billion transistors. That's more tiny switches than there are people on the entire planet, all crammed onto a piece of silicon smaller than your fingernail. The scale of it is just, it's staggering. And right there, that's the core of the problem. When you're working at that tiny, tiny scale, nothing is ever perfect. Every single one of those billions of transistors has little random flaws, tiny variations. Most of them, totally harmless. But every now and then, one of those tiny imperfections can cause a circuit to mess up or even fail completely. So the question is, how on earth do you test for every single one of those possibilities? You can't. Well, the old school way of doing it is something called a Monte Carlo simulation. Just think of it like rolling the dice a million times to see all the possible outcomes of those tiny flaws. It's a powerful tool for sure, but it has one massive weakness. It needs a ton of data from real physical devices to be accurate. And if you're working on something brand new, something experimental, well, getting that data is a huge bottleneck. It just grinds innovation to a halt. So, how do you get around that bottleneck? How do you get all the data you need when you just can't? Well, the answer is just so clever. You teach an AI to dream up the data for you. Let's see how this whole thing actually works. And this is the magic right here, generative modeling. It works like this. You give the AI a little bit of real data to look at, the AI studies it, and it learns all the underlying patterns and rules. Basically the essence of what makes that data, well, that data. Then, once it understands, it can start creating completely new examples, endless amounts of them, that are totally fake, but are statistically identical to the real deal. You've probably seen this in action already. You know those pictures online of people who look totally real, but they don't actually exist? They were dreamed up by an AI? That's a generative model. The AI was shown millions of real photos, learned what a human face is supposed to look like, and then it created a new one from scratch. We're doing the exact same thing here, but instead of faces, we're talking about the electrical behavior of transistors. We're creating fake transistors that act exactly like real ones. Okay, so we've got the concept down. Let's circle back to our original problem and see how researchers actually used this dreaming AI to tackle that huge challenge of chip variation. The process they came up with is just brilliantly straightforward. First step, characterize. You just take a tiny sample of real transistors. We're talking as few as 20 or 50, and you measure their properties. Step 2, train. You feed that small chunk of data to the AI. Step 3, generate. You tell the now trained AI to create a massive new data set with thousands of these virtual transistors. And finally, step 4, simulate. Use that huge, rich synthetic data set to run all the circuit tests you could ever want. Now that all sounds fantastic on paper, but the big question is always, does it actually work? So to find out, the researchers decided to put it to the test. They pitted their AI-generated data against the industry-standard simulation models using a really common test circuit. And the results are, well, check this out. This table compares the AI model to the industry gold standard, which is called BSIM. Look at the far right column. That's the reference value, 8.63 nanoseconds. Now look at the middle column, specifically that highlighted row. That's the AI model, trained on just 50 real devices. And its prediction? 9.04 nanoseconds. That is incredibly close. And remember, it got there from just a tiny, tiny initial sample. And it wasn't a one-off. The accuracy holds up across different measurements, too. Here, we're looking at power consumption. The bar on the left is that same BISIM reference. The bar on the right, that's our AI model, again, trained on just those 50 devices. Look how close they are. This really proves that the synthetic data isn't just a party trick. It is a genuinely accurate reflection of reality. Okay, so full disclosure, there is a trade-off. Right now, the AI model is a bit slower for each individual simulation than the standard model. But, and this is really the whole point, the standard model needs huge amounts of data just to get started. The AI's power, its revolutionary advantage, is that it can build these incredibly accurate models from just a handful of real-world samples. It makes the impossible possible. So yeah, this is a total game changer for designing computer chips. But this whole idea is so much bigger than that. This is a fundamental shortcut that's starting to completely transform all kinds of different scientific fields. Take particle physics at CERN, for instance. Researchers there need to run these unimaginably huge simulations, but they are incredibly slow and expensive to run. So what do? They train a generative AI on a small set of real simulation results, and then they use it to dream up all the extra data they need. It lets them test out new theories in a fraction of the time it used to take. Or think about biomedical research. When you're designing a sensor that's so sensitive it can detect a single molecule, any tiny bit of electronic noise can completely throw off your results. It's a huge problem. But with synthetic data, engineers can model all those complex, random variations, and that helps them design much more reliable and sensitive medical tools. We're talking about things that could lead to huge breakthroughs in healthcare. Okay, so we've seen this clever shortcut in action in semiconductors and physics and medicine, but what does this all really mean? Why is this such a game changer? Let's bring it all home. I think this quote from the research paper really says it all. It says that getting data from just 20 to 50 transistors is often feasible, even in cases of emerging devices or ones working in a cryogenic cooler. What that really means is that this whole method works for technologies that were basically impossible to study statistically before, things that are brand new, experimental, or operating in really extreme environments. It just blows the doors open to whole new areas of research. And here's the bottom line. This isn't just about innovating new things anymore. We're now innovating how we innovate. By creating these incredibly rich virtual sandboxes from just a tiny bit of real data, we can try out more wild ideas, we can fail faster, and we can learn quicker. We're accelerating the entire process of scientific discovery itself. And that leaves us with one last really big question. This technique isn't just for transistors or particles. It could be used for drug discovery, climate modeling, developing new materials, you name it. So if we can create a high-fidelity digital twin of pretty much any complex system from just a few real-world samples, what impossible problems are we going to solve next? The possibilities really are endless.